So, what are we doing in this chapter? We are doing duct, adiabatic duct with friction. Okay? So throughout this duct, basically as the flow is going like that, the flow is going this way, there's friction acting on it. Alright? This duct have a diameter D and have a length L and have friction F. And most of the time you will be asked, basically you'll be given one of those two things, sorry, two of those things, either M1 and L, and he's asking you for what are the conditions at the exit, or you could be given the inlet and the outlet and he's asking you for the geometry, right? And we said this on a TS diagram will look something like this. This is the sonic point. And so if you start here, subsonic point 1, you will basically go to point 2. So point 2 could, but point 2 basically could be like this, or if the duct is long enough, you could even hit the sonic point at the end. So the point, the sonic point, let's call it the start, it's measured basically by the distance it takes condition 1 to reach. And we call this L max 1. And so the same point can be reached from 2 using L max 2. That's the length. So let's call it 10 meter, and this is 2 meter. So obviously the pipe is 8 meter. Appendix F will give us this L max as function of M2, and this L max as function of M1 by appendix F. Right? And that geometric effect, which is to go from here to here, is much longer than to go from here to here by the pipe length. This simple geometry is the equation that you will always use. Right? Which basically say L max 1 is L max 2 plus the L. But rather than just saying it L, we also add F. Right? So we say F L max over D1 is equal to F L max over D2 plus F L over D. So again, you could be given the initial condition, the geometry of the pipe, and he's asking, well, so how long, or what's the exit condition? Right? We can be given the inlet and the outlet, and he will ask about this. So again, anytime you see this equation, I want you to think that this is as if I have M1. And this is as if I'm having M2. Right? We will have to use this equation. Every single tunnel flow problem, you will have to have this equation. So the moment you hear friction, just write this equation. You guaranteed yourself 3 out of 5. No, right? Because, I mean, this is one equation that's correct. Right? You read friction, you write this. 3 out of 5. That's a D.
Next problem.
Next problem, yeah. Right? So in that, let's review this problem very quickly. We solved this problem before, right? So here is the inlet condition in the tank, which is not exactly 1. You know, if you have P naught and T naught through this isentropic nozzle, it's not P1 and M1, right? But if we have M1 here, we can solve this nozzle and get from P naught and T naught, we can get P1 and T1, right? From appendix P. So we don't have the condition, but we could easily if we just have M1. And he said he would like to find out how much mass flow rate to basically, what is the maximum mass flow rate through this pipe, right? And the back pressure for that to happen. Obviously the back pressure or the pressure at the exit need to drop a little bit in order to generate this maximum flow rate, right? So how low it should be in order to generate this mass flow rate? So for the maximum flow rate, that means that if I plot the pressure distribution, you know that we can get higher and higher flow rate as basically we drop the pressure lower and lower, right? The more you drop the pressure at the exit, the higher the flow rate. But up to a point, and that point is when I cannot just keep dropping that pressure forever and expect the mass flow rate to increase more and more, right? There is a limit. What's that limit? Huh? Right, Mach 1 here. If you get that star, and so V back is V star, that's the maximum you will be able to generate. Because you know that if you drop this back pressure any lower, this guy cannot do more than one, right? He cannot. All the people before the level could never really accelerate a flow through a duct or through a nozzle more than one because they didn't have the diversion part. So that's the end of their dream, basically. All right? So for this problem, to get this to be M equal 1, that would correspond to the maximum back pressure, right? And so he's asking for what is that pressure to do this, and what would be the M dot, say M dot 1 or M dot star over here, what? It's the same thing, right? What is the M dot that will do this? So to solve this problem, well, we realize that if only we have M1 or M2, because we have the geometry. So according to what I said, he will always ask us for one of those two things, and he will have to give us the other two. He will ask us for one, and he will give us the two of them. So FL max 1 is FL max over V1 plus, so that's 2 plus FL over V. So since I have this, I just need one of them so I can calculate the third. Which one do I have in this scenario? 2. 2, I have 2 because he said he wants the maximum flow rate. Therefore, what's your name again? Nick said, therefore this guy is sonic. Therefore, 0. The FL max over D 0 because the Mach is 1. So yeah, we got 2 of them. Therefore, we can calculate the third, which if you calculate this and you take it to appendix F, this is basically M1. And so knowing M1 is enough to basically give you P1 and T1, because again, you know P naught and T naught. And so now you have M1, P1, and T1, you have the mass flow rate. And time to get the B star. Well, from the Fano duct, M1 is also in the Fano duct. So M1 is what's joining those two flows, the isentropic flow and the Fano flow. So from M1 and the Fano duct, remember the TS diagram? So here is 1 and here is the start condition, which is 2. From the Fano duct at M1, you can get P1 over B star. And since you know P1, then you know P star. Right? And you are done. That is the pressure that will make M just 1. And lowering the back pressure any more than this will not really improve the mass flow rate. Alright? Correct? But what if the back pressure is higher? So what I'm saying is, say the back pressure is 0. What will happen? What happens if the back pressure is 0? Choke. This guy is choked, nothing will happen here. And outside, what will happen outside? Expansion fan, right? Expansion fan will grow like this, so that the flow will come here and will basically get lowered to the whatever the pressure outside. And of course his Mach number will increase. Right?
You don't have an expansion fan there?
Huh?
You don't have an expansion fan?
Yes, you have expansion fan.
Oh, yes, I'm sorry.
At the exit, you will have 2 expansion fans. Right? So that's what he was trying to say over here. We want to solve for M dot if the duct in the duct for the nozzle, since they are the same, what should we do? And P1 over so You can solve this. We know the area and well, let's not do this one. It's actually over here. All right. So that's what we were trying to solve. So here is the pressure T01 and T01 and B back, and B back is 101, and that's higher than the B star. This will not choke the nozzle. So this example is exactly a situation like this, where the B back is not small enough to make the Mach number basically choke. So what do you do? So this is a new problem. We don't really know this for a fact. I mean, he just threw us a B back on us. He didn't say what is the back pressure to choke the nozzle. He just said, here's a B back, 101. Give us the M dot. So I need first to come up with this, B star. So I can tell myself, am I above or lower than that B star? If I'm above, then B exit is B back, and we'll do it exactly like this. And if I am lower than B star, then forget about B back. B exit is B star, right? The nozzle is choked. The M number is 1. The Mach number is 1 at the exit, right? And we have the maximum flow rate. So, of course, the first thing is to write that equation, right? And to realize that, well, I have this, but I don't have the Mach number at the inlet or the Mach number at the outlet. So I will try to get the Mach number at the outlet by this P over B star. So therefore, let's get B star, right? So how you get B star? Say that again.
Right, the equation.
This one, right? And then
Max 2 is
0. Right. Make this guy 0, and therefore tell yourself that Fn max over D is equal Fn over D, and that will allow you to get. Not yet. This allows you to get M1, right? To start, they allow you to get M1. And therefore, what if you know M1? That's how we get the M1 to start with. Right. So once you know M1, from final flow you can get B1 over B star. That doesn't really help that much yet because we don't know B1 or B star. But you also go back to this nozzle and get B1 over B node. Now you have B1, now you have B star. Yes, Andrew.
Forgive me, but how do we know FL over D to begin with? Are we given all those values?
Right, so again, we only know the pipe, FL over D. Okay? We only know the pipe. We don't know M1, we don't know M2.
I didn't see that in the friction. That's all.
Right, the friction is given, right. The friction and D is given, the L is given. The only thing is M1 and M0 and M2 is not given. And we are solving it for a certain back pressure. But to start with, we are trying to figure out, so what is the P star so that we would know, are we here or there? Are we choked or not? Is the Mach number at the exit 1 or no, it's not, and it's less than 1. So let's get P star. So to get B star, John said, let's write the equation. I wrote the equation. Here it is. Okay, what I know, geometry, M1 and M2 are not known. So how we can get B star? Let's assume it's choked. Let's assume it's choked. M2 is 1, therefore this guy is 0. Therefore, this is Fn over D. The L max 1 is L. The L max 1 is L. You can get M1. Now once you have M1, the flow, the Mach number in the pipe, at the beginning of the pipe, this allows you to go and get P1 over P star, and this allows you to go back here in the nozzle, appendix P, and get P1 over P01. So from the nozzle you get P1, and from the fan of flow you get B star. You got your B star. How much? It turned out B star is, so actually in this particular problem, B star was 450, and therefore 101 is actually choked. So 101 is less than 450. So this is choked. Therefore, since it's choked, so in M dot you can basically get it from that M1 that you assumed. The M1 that you got from assuming choked duct. Okay? And if it wasn't, if the number was higher, we will do what we did here. Okay? Question so far? So as long as you really understand this equation, this chapter will not really be confusing. Okay? So we will get a little bit more complicated in a second. So, but before we leave, I want you to be happy with this equation. Any question about this equation? This equation is simply telling us that from 1 to start condition, we call it Nmax 1. From 2 to the start condition, we call it Nmax 2. The difference between them is the length of the pipe. Right? Very good. So now what happened? Now we have a diversion nozzle with a funnel duct, not just a conversion nozzle. Okay? So in the conversion nozzle, we had only one scenario, and that is the duct will be choked at the exit. You will hit Mach 1 at the exit. There's no other place where you can go to Mach 1. But with a diversion nozzle, he actually could hit supersonic flow in this conversion nozzle. Right? But for that to happen, then he shouldn't hit Mach 1 here before he hit this place. Right, so what I'm saying is that if the duct is really long, imagine this funnel duct is really long, so they had this diversion nozzle at the machine room, third floor near the auditorium, and then a very long duct until we come over here. And so initially the pressure is the same, and then we start lowering the pressure at here in this room, the back pressure. We take this pressure here and lower it. Chances are, if the duct is really long and there is a huge pressure drop through this duct, chances are we will hit Mach 1 here before the nozzle, the diversion nozzle, even have a chance to go to M1 at the throat. Right? But if the duct is short, if the distance is short, then maybe the duct will actually hit, he will allow the nozzle to come to supersonic velocity before he can get choked at the exit. So there are two cases, all right? So very long duct, and by very long, we basically mean that the length is bigger than the Nmax 1. All right? So this duct, basically, he will be choked first before the nozzle. And the second case is the short duct. So now here is a short duct connected to a convergent diversion nozzle. So what happened? Here are the different scenarios. So first of all, the trivial solution, P back equal P naught. Obviously, same pressure everywhere, no mass flow rate. Okay? And then you lower the back pressure a little bit, the flow will accelerate a little bit in the nozzle. Maybe you hit Mach 0.2 or 0.3, well, still subsonic. You go into the diversion part, he decelerate because that's a diffuser for him. And you come here in this nozzle, in this duct, and he's subsonic flow in a funnel flow with friction. So what happened? Pressure drop. Right? And the scenario keep going until you even hit Mach 1 at the throat, but you still subsonic because of the back pressure. So you go back subsonic, you go into this duct, start as subsonic, and your pressure will drop, but you leave a subsonic flow. And so the extreme case for that is a very long duct where basically you can even hit Mach 1 at the exit in this subsonic funnel duct. Right? But if the back pressure is low, that make the duct short because the back pressure is low for this pressure combination. So what will this do is actually make you go supersonic all the way, even to the design condition. And then now you go into a duct as supersonic flow. You go to the duct as supersonic flow and look at that. The pressure actually go up rather than the pressure dropping for a subsonic flow. Supersonic flow will have pressure rise in the duct. Okay? So here is the subsonic and here is the supersonic. So if the back pressure is sitting over here, perfect, you get supersonic solution. If the back pressure is over here, you get the subsonic solution. What if the back pressure is in between? You will actually put a shock wave in the middle, because that supersonic flow will keep going up to a point where he basically say or figure out there is actually a very high pressure in front of him waiting, and so he goes subsonic, and that's when we jump. When this happens, because it's the same M dot. Yes, you have a shock, but the M dot in the duct before and after the shock is the same, because the shock cannot store mass flow rate. There is no storage. So you will jump from here to here, and then you keep going. Okay? And it's that scenario where you have to realize that I have the same mass flow rate, I have the same B star for the supersonic branch and subsonic branch. Alright? That's how you connect the two problems together. Alright? And the position of the shock, of course, depend on
The back pressure.
excellent, the back pressure. So knowing the back pressure, you should be able to find where the shock is. Okay? However, the equation in our textbook is written such that this would require trial and error. It's not straightforward. I mean, there is no one equation which will tell you if the back pressure is this, the shock is in the middle. So if this is the case, you know, if you actually, he's giving you the back pressure and he's telling you, now find where is the shock. Is it after half meter or 3 meter, or this become the most difficult problem in this course. Right? The easy part, or the easy version of this one, is that if I give you the location of the shock, if I say the shock is in the middle, or the shock is 30 meter from the inlet, what is the back pressure that did this? That's straightforward. Alright? So we'll see how we can solve both of them. But anyway, Shen is right, and the location of the shock depends on the back pressure. And so eventually, if the back pressure is low enough, you can pull the shock wave all the way to the exit. So that's a normal shock at the exit. Right? After this guy, if you take the back pressure and you lower it even more, what will happen? Oblique shock waves outside. And then kind of the design condition of the supersonic exit, and then expansion fan comes out. Right? So expansion fan, perfect expansion, oblique shock wave, normal shock wave at the exit, and then normal shock wave inside. And so sometime in the problem you would say, what is the back pressure that will result in shock wave inside the duct? That's actually a range. It starts from here, that's the first point, up to what is the back pressure that will result in a normal shock inside the duct. From here all the way to
Subsonic solution.
no, a little bit lower than that. What is the back pressure that will result in a normal shock inside the duct, not inside the duct and the nozzle? So what is the last point? It's the point where a normal shock appears at the exit of the nozzle. With that Mach number here, the supersonic Mach number. Okay?
So on a short duct, it can leave supersonic.
Say that again.
In like a short duct, it can leave supersonic.
Yeah, you can. But a long duct, you would never leave supersonic, because the nozzle never get the chance to get Mach 1 to start with. But a short duct, you can leave supersonic, right? You can leave supersonic, you can leave subsonic because there's a shock inside it. Right? So it's a combination of the length and the back pressure, not just the length. Because obviously a short duct with back pressure equal to B naught, that's not even a flow. There's no flow at all. So you need the right combination of the back pressure and the length. Right? And again, here I'm trying to explain, so how come a supersonic flow eventually see, I said before that he doesn't see and he wouldn't see the back pressure. Yeah, you cannot expand him, but you can stop him. So if the back pressure is higher, I mean, he cannot ignore it. Just again, this example where I'm saying, you know, a supersonic flow cannot ignore a wedge in front of him. I mean, eventually he will have to put a shock wave on it, right? If you have a resistance, the molecules are stopping in front of you, they're accumulating, you cannot just run over them. I mean, you have to stop for them, right? And that's what's happening. So this back pressure will stop those guys, and that's what eventually makes the supersonic flow stop or turn to a subsonic, right? And so the normal shock inside the duct, here is this example. You basically find the back pressure for a normal shock inside the duct. So here are the two extreme cases. Normal shock at the exit of the duct, normal shock at the inlet of the duct. And between the two of them, that is the range of back pressure that will put a normal shock inside the duct. So how come I'm drawing this too big and this is too small? Why this shock need to be really that strong and this shock is kind of like weak? I'm measuring the strength of the shock by the pressure ratio. So why this guy have so big pressure ratio and this guy have very small pressure ratio?
Because there's a bigger pressure jump earlier in the duct because the pressure increases.
You're answering me. I'm saying why the pressure is high. You're telling me the pressure is high because the pressure is high. No, why is the pressure high here compared to this? Excellent. Excellent. So how come this Mach number here is much bigger than the Mach number over here?
Because the flow is decelerating.
Right, because the flow basically, supersonic flow, yes, but you know he's going to a duct with friction. His Mach number is dropping. The pressure is getting higher. So if this was like Mach 5 or something, this is probably Mach 1.5 now. Right, because of all that friction in the way. So, you know, eventually a shock wave on Mach equal 1, that's not a shock wave. That's basically a Mach wave. That's isentropic flow. But shock wave in Mach 3 or 4, that's huge. Right? Very strong shock.
Those always
Actually, this is not an oblique shock. This is a normal shock. So with a normal shock, we don't have a choice between is it weak or strong. Right? In the exam today, you know, that question always rises. Is it a weak solution or a strong solution? Right? And the reason, the answer is, if things are flying in air, no way there will be strong solution. It's weak solution because there is no wall. And even with wall, if you have a problem with wall, and now you are asking, well, is it weak solution or the strong solution? I see walls. I have the potential to make it strong solution. How could you tell if it's weak or strong?
Mach number after the compression.
Right, excellent. If the Mach number after is supersonic, that must be weak. How could you tell that the Mach number is supersonic after the shock? I mean, you look at the problem, how can you tell that the flow after the shock is actually still supersonic?
It would depend on the wave angle, like the shock angle.
Right, if you see a wave reflection, for example, after it, that must be basically a supersonic flow. That's why he got a wave after it. Like the homework when we had 5 oblique shock waves. I mean, obviously it's supersonic because of all the waves that he's going through, right? And by the way, if we already established that after, say, 2 of them, the flow is producing the weak solution, chances are he will still keep going through weak solution one after the other. Why? Because obviously that backflow, the engine outside or at the end of the problem is not really a big resistance to the flow. So you can, what I'm trying to say is that you cannot basically expect 2 weak solution and then strong solution. Why? What happened? It will just keep going weak all the way. All right. So in this problem, let's solve one of them. Alright, so here is a supersonic expansion all the way, right? And let's basically figure out let's do number one first. A shock wave standing here at the inlet of the duct. And so turn the flow subsonic, and therefore you basically drop like this. Okay? And we are asking for the B bit. What are we given? B note, and the nozzle here, the area exit over area star, or area exit over area stroke is given to us, and Fn over V is also given. Alright? And so I'm going to call this 1, and this is 2, and this is exit. And so required is B exit, which is equal to B bed. Can anyone help me? Say that again. Excellent. You will do really well in the final. So the final has a fan of flow problem, right? Cool. So FL max over D1 equal to FL max over D2 plus FL over D. And I know the length, okay? But actually, since we call it 2 and E, let's call it 2 and E, right? 2 and E, right? And by the way, how does here's the diagram look like? It'll be something like this, and that's the start condition. And supersonic turned into subsonic. So this is 2, and this is E somewhere over here. I don't know if that's gonna go star or not, right? So one would be something like this. One would be here. So can anyone help? Excellent. So from the nozzle side, area exit over area slope, this should give us M1, and it can also give us, not yet, this area ratio can give us M1, and it also can give us, excellent, P1 over P01. Right? And you have P01, you can basically get M1 and P1 from there. Very good. Okay, then what? We solved this part, right? From the conversion diversion nozzle, we managed to get M1 and P1. M1 and P1, we have them.
Well, since we know there's a normal shock.
Right, and therefore I can take this M1 into a normal shock table, and I can get what? I can get M2, I can also get P2 over B1, right? P2 over B1, and since we know P1, we can get basically B2 and M2. So we now start a fan of flow with M2 and B2 given to us, and we are asking about, well, M exit, but not really. We really want just B exit, but chances are we need M exit to get B exit. Right? That's a fan of flow duct. problem, where the inlet is given, the geometry is given, and you want the exit condition. How do we do it? We go to this equation, we tell ourselves we need to know two of them, and we can calculate the third. Since we want to calculate stuff at the exit, then we have to know the geometry and the inlet. Do we know the inlet? The FL max 2 over D. Do I know this? How? How? From M2 and appendix F. Then you know this guy. And you know this guy, you can calculate FL max over D. FL max over D at the exit, and from that to appendix F you can get M exit, and you can also, you don't really care about M exit, but you care about, once you have this line, once you know where you are in the table, you can calculate what from this? B over B star. B exit over B star, right? At that Mach number. And you can also, from this guy, not only you get this length at M2, but you should also get B2 over B star. Right? And this will allow you to get B star. So the cartoon that I always love to draw is, it's this, that if we have a final that, here's 2 and here's the exit, or here's 1 and here's 2, we always go and solve for the B star, and then we use it to calculate this. So knowing the pressure at the inlet, you will calculate the pressure using M1 or M2, the Mach number at the inlet. From appendix B, you can calculate the B star, and from that, you can calculate the pressure at exit. Okay? Does this make sense? It's really this equation, which allow you to get the Mach number, but also to allow you to get the pressure, using B star as a stepping stone for the solution. Okay, so let's look at the solution. So this is what he did. He wrote the equation. He said, well, he called actually 1, 2, and 3. That's fine. So he said, well, I don't know those two guys, so I need to get one of them. So he go to the nozzle, get M1, solve the normal shock table like what Kenny said, get M2 from the normal shock, and from M2 now he can go and get this length. Now the only thing is missing is this. Calculate this guy, he calculate his Mach number at the exit, 0.54. He also do the pressure. He get the pressure from the isotropic nozzle, solve the pressure through the normal shock table, and from M2 he can get B star, and from M3 he can get B star over P3, and that allow him to get B3. Okay, questions? Is it hard to solve this problem? Alright, let's solve the other one. So this is the other extreme, a shock at the end of the duct. Shock at the end of the duct. Supersonic expansion, right? But then the supersonic flow keep going until the end where you have an oblique shock, a normal shock standing over here. So that's why this, right? And so 1, 2 just before, and 3 just after. All right? And again, B naught is given, area exit over area sort is given, and Fm over D is given. And required is B3. So B3 equal B back. So I'll do the first part first. You know, area exit over area throat, you will get through appendix B, you can get M1 and you can get P1 over P naught and not P naught 1, and that allows you to get P1. Now you have M1 and P1. What do you do next?
From M1, we're going to go to the appendix F.
Appendix F, and this allows you to get FL max over D1. That would be supersonic. And you write this equation. You know the stuff at the inlet, you know the length of the geometry, you can get M2, which will stay supersonic. And with that, you can also get B2 over B star. Right? And by the way, over here also, you should get B1 over B star, which will allow you to get B star. And so from this, then you can get B2. Right? And on the TS diagram, what happened? What happened is we are moving from here to here, from 1 to 2. 1, 2, and then we're going to jump to 3. Subsonic.
That P star is that from the appendix F? The P star at 1.
Say that again.
When you're saying we solve the P star at 1, would that be from appendix F, the P over P star at appendix F?
Correct.
Or M? Okay.
Correct. So M1 from appendix F, you can get FL max over D, but you can also get P1 over P star. So that P star, that is this point, that is the star thing here. Right? You needed to get P2. Remember that sketch, can you see it from there? From 1 or the inlet, you can get the star. From the star, you can solve for the exit.
Is that not exactly what we just did?
That's exactly what we did, but now the numbers are supersonic. But that's exactly, so Tommy is saying solving a supersonic duct is exactly the same as a subsonic duct. What's the difference? There's nothing, except that the numbers are going to be bigger than 1.
The other one is B.
Right. Right? So rather than we were here, now we are here. So we are still approaching the start condition, but from different range, basically. Rather than accelerating, accelerating, accelerating to the start, we are decelerating, decelerating, decelerating. Okay? Except that for the supersonic thing, we cannot decelerate all the way to 1. A supersonic flow cannot just keep dropping until he hit 1. He will have to jump to a subsonic flow before he can go to 1. Okay? So we managed to get B2, we need P3. Kenny? Right, normal shock table, just like the previous time, right? So if you know the Mach number at 2, you go to normal shock table and you can get P3 over P2, and you're done. Okay? And so again, this is what he did. So at M1, he's getting it from the nozzle. Use appendix F to get the FL max 1.36. He used this equation. He got the geometry. He got the inlet. He can basically calculate the exit. So the FL max over here, the exit is 0.16. It's smaller, right? Because we are getting closer and closer to Mach 1. So from that, he calculates M2. So M2 is what? 1.56. So he dropped from 2.19 to 1.56. From 2 to 1.5. And then he calculates also B3 over P2 from a normal shock table. This pressure ratio, okay, from M2. And he will get PC if he just know P2, and he get P2 from P1 over P star and B2 over P star. All right. I just need to warn you about something. So, in the book, when he tried to get say B3, you will find it like this. Every year the students get confused and he come tell me, what is that? How do you? So they would say in the book he would say B3 is B2 over. It's no. So that's B3 over B2 times B2 over B2 star multiplied by B2 star over B1 star multiplied by B1 star over B1 multiplied by B1 over B naught 1 multiplied by B naught 1, which is okay, right? Which is okay, but the problem, so what is going on? Well, this is actually, I mean, this is 1, and this is from M2 appendix F, and this is from M1 appendix F, and this is from the M1 appendix P, and this is given, and this is normal shock table, appendix C, M2. That's okay, but the problem I have with this is that the students basically, then in the exam, they try to solve a problem like this. So they would say, oh, you need B3, okay. So B3 is B3 multiplied by B2 over B3 multiplied by B3 over B1 multiplied by B last year over B new next year. And they start cooking the number as thinking that, well, as long as you repeat the number, then it's okay. And right? And so then eventually they like, so how can I get this B1 over B3? There is no B1 over B3. There is no relation between P1 and B3. They're never really part of any combination. So there is nothing wrong of writing it this way, but I really rather you looking at the geometry and realizing that I need this. This is normal shock table. Obviously, I need the pressure before it, so I can solve the normal shock table. Therefore, I need this pressure. How can I solve that? That's the exit of a Fano duct. I better solve this Fano duct. From B1, I can get B star, and from B star, I can get B2. I need P1. How can I do that? It's part of the nozzle. Let me solve the nozzle. This is much easier, and you will not go wrong compared to this. Right? But if you know what you're doing, go ahead and do this. But don't expect that writing any numbers will solve the problem. Right? What's hard about the solution of the book, when you do it like this, then the next line, you actually start seeing the number. It's 101 multiplied by 0.47 multiplied by 0.3914, and so this is like, what? How is that? What are those numbers? Where did they come from? They came from, he's solving a normal shock table, he's solving the Fano flow, he's solving the isentropic nozzle, so that the solution doesn't detail where those things coming from. So it's not really a shortcut. It doesn't make the solution easier. It actually makes the solution more complicated. It makes the grading also even harder, because then someone grading your homework doesn't really understand what's going on. Where those numbers came from. Did you actually use the normal shock table?
So page 303, just cross that.
Show me. Right, so that's on page 303, correct? That's the way he... But again, if you understand what's going on, go ahead and use it. Page 303. That's what's going on over there. But I don't think it really helped in the solution. Why? Again, because the students are tempted to put any kind of combination, thinking that eventually they will manage to get them. And sometimes you can't. All right. So here's a choke duct, and L greater than L max. I is the inlet. So the nozzle, the nozzle is choked, meaning you can actually have supersonic flow, and supersonic flow is leaving. But because the duct is so long, it's bigger than this length at the inlet, Li, so let's call this Mi. Because the duct is much longer than this Mi, the supersonic flow cannot just keep dropping until you get M1. Then what? What happened after you get M1? So because of this, he basically go to a shock, become subsonic, and then adjust to the length of the duct. Right? And so he can go to a shock and then leave subsonic with Mach 0.3 or 0.5. Notice that when he becomes subsonic, what happened to his Mach number from this point on? Once you become subsonic,
It increases.
it increases, and so you can actually hit Mach 1 at the exit. Right? If the duct is long enough or the back pressure is low enough, or the combination, the duct is long and the back pressure is low, you turn into subsonic and then you accelerate to M1. So your question to me should be, so if the pressure is so low, 0, what is this guy problem? Why he's going through a normal shock? I mean, you said he have a normal shock because there's a high pressure in front of him and he see that he cannot really go through this high pressure. That's why he turns subsonic. But if the Mach number is 0 at the exit, why he's going through a normal shock? What is his problem?
Because you would reach the star condition.
Right, because the duct is so long that he cannot really hit the star and then just keep moving at the star. Right, that's why. So really, the duct is being long. You know, when you think about it, what is the resistance we have? It's FL over D. It's that number, that combination. If L is really big, or F is really big, or D is really small, that is the resistance that make it really hard for the duct to go through. All right? So when this happen, again, the first part is supersonic. He jump to subsonic, and then he keep going subsonic until he hit the star at the end. Right? And again, the whole thing, supersonic and subsonic, they all share one star point at the end. So B star here is the B star here is the B star here. Right? And if he hit Mach 1 here, this make basically the second equation have 0 for a lens at the exit. Right?
How would we know when our P star changes? Because you're saying this is all true, because if our P star is the same. But
as long as it's the same mass flow rate, it's the same TS diagram. That TS diagram is for the same mass flow. You remember how did we make this guy? It was the mass, continuity equation, and conservation of energy. That's how we plotted this guy, without even considering the momentum equation. So as long as the M dot is the same and the duct is adiabatic, you didn't allow any heat transfer in or out, you are on the same curve, you have the same star condition at the end. Okay? So here is the hardest problem in this course. Locating a normal shock in a Fano duct connected to a converged diversion nozzle. Of course, if he wasn't connected to converged diversion nozzle, there will be no Fano, there will be no shock waves. Convergent nozzle will never make supersonic flow, therefore there will never be a shock wave, right? So you have to have converged diversion nozzle to have supersonic, therefore to have a shock. So how can we find the location? So here is the problem. So find the location of the shock, say for back pressure equal 0 or back pressure equal 180. Where can we find the shock? So here is the convergent diversion nozzle connected to basically the two ducts, the supersonic and the subsonic. Right? And on the TS, the pressure distribution first will be something like this. Right? And then because the flow is supersonic, he will go up and then shock wave. Right? And then he will drop down. And so if I call this, what did we call it? I, 1, 2, and exit. And notice how 1 and 2 are connected to each other by a shock wave equation. If you know M1, you will be able to get B2 over P1.
Normal shock would move the pressure up, wouldn't it, rather than down?
Sorry, John is right. I knew something is wrong.
Is this assuming subsonic flow after the shock?
Say that again.
This is assuming subsonic flow after the shock.
So a shock will never produce, this is a normal shock, so it will never produce anything but subsonic flow. This is not an oblique shock. This is a normal shock sitting inside. And so the problem is, what is that length? L, E, Li, Li2 or Li1. It's the same. So how much is that length? So what will be given is, of course, the nozzle and the FL over D, right? And P naught and P back. So what's your plan? So here's the question. How much is that length? Steven, how do you get that length? Steve, write the equation. That's what I'm write the equation.
Yeah, well, you start with the equation.
Right, and that's the solution.
Yeah.
Li max over Di equal to FL max over D1, right? Plus,
LD.
huh?
FL over D.
Which L? I1, right? Because this is for the first duct. And so this is what I want, therefore you need to give me those two guys. This is given from, how can I get this guy at I? I can't see it.
PR? Does it give us the,
It gives you the nozzle geometry.
yeah. Yes.
We can find M1 or MI.
So MI, of course, the nozzle geometry, right?
Yeah, good.
Appendix B, you can get MI. So we have this guy then. So two unknown, right? Doesn't work. Since this is really the real unknown, then I have to get this guy. Anyone can help me getting this guy? Or basically, I'm asking for M1.
Yes, the next one.
Huh?
Yes, the next one, the iterate.
What's the next line?
The LI1.
You want to guess this so that you can calculate this?
Yeah.
And then how do you check on your answer that your guess is correct?
You have to do the second one next and then compare.
That's an excellent approach. So John is saying, well, since we have two unknown, maybe you can guess this guy. But then I asked him, if you guess, you need to be able to check on your guess and say, well, was this a good guess or not? So if you assume the location of the shock, you should be able to solve for M1. And if you solve for M1, then through a normal shock table, you can solve for M2. Right? And now if you have M2, it's a guess at this point. How can you tell that this M2 is good? He said solve the second part. So the second part is exactly this equation, but for L max over D exit equal to sorry, it's 2, guys. FL max over 2 equal FL max over D at the exit plus the FL over D, and this L is 2E. But at this moment, it's known because we assume this guy. So since we know this guy, and we know this guy, we can actually now solve for M exit. You get an M exit. How do you check on that assumption?
C onto G star equals the.
Excellent. Solve for B exit. Using this guy, solve for B exit. You basically solve for B exit for B star, and from here, you will also get B1 over B star. And you have to realize that it's this B star that we had it in the first part. It's the same B star. Actually, let me go to that's important. The same B star that we got it in the first duct, that's the whole key to the problem. So when we went from I to 1, and then we went from T to E, they were all basically talking about the same star. All right? So then you calculate this P exit. But obviously, this is a huge trial and error and it's expensive. Expensive time-wise because you're solving two final duct with a normal shock in between. And so now what if, no, the B exit is a little bit higher than B back? We go back again and we go again. So they, in the book, they realize this. And so they basically figure out that so here are the two lenses basically. They just put the two equations together. And then they said, well, so obviously it's this two duct with a normal shock table. Eventually, those three equations is enough to close the system, but it's the way the equation that's written that doesn't allow us for us to get the answer explicitly. All right? So, what should we do? They basically said, well, let's put all the equations together into one equation where there's only one unknown, really, which is, say, the M1, for example. Right? So here is this equation. So this is equation 933. This equation, which is 933, is described, it's a big function of M1. Huh? This equation should allow you to get M1. It's non-linear equation, right? We can leave it for the extra credit for 3013. I'll give it to them for extra credit, and then I'll ask them to plot the curve for you guys, and then the best curve will take it here to solve the problem with. But it's basically solving this either non-linearly or graphically will allow us to come up with M1 out of that. But I need to know the left-hand side, right? What is that left-hand side? It's basically this. It's FL max over 2 minus FL max over D1. So, sorry, it's actually this. It's also this. So it's FL over D plus FL max over DE minus FL max over ID. So this is how you solve with minimal iteration, you can basically get M1. So again, we will have a graph for this, okay? And make 3060 students do this for you. But to solve this, you need to provide the left-hand side so that you can solve from the chart if the M1. So this guy requires those three numbers. Mach number at the exit, Mach number at the inlet, and the length of the pipe. The length of the pipe, we have it, right? That's what the problem started with. That's the whole length of the pipe. The Mach number at the inlet, we will get it from the nozzle geometry, right? How about the Mach number at the exit for a free homework problem? Don't hold on. If you know the answer, say. Don't wait for shame. The question is, I would like to use this because that will tell me the M1. This solving this equation, this will tell me M1 if I only provide the left-hand side. The left-hand side is basically three numbers. The geometry, I have it. The Mach number at the inlet, so appendix F, I can get this, and
Back pressure.
Mach number at the exit.
Is it from the back pressure?
What do you mean? Just give me M exit, you get your free homework. What do you want? Let
Is it
Jason
choked
get
at,
it.
is it choked at one?
No, it's not choked. No one said the exit's choked. What we know is the B back and B node.
So you can use that to go to the table and find the ratio of the pressures, and you can figure out the map number from the Fandom table.
Explain slowly what you want. What do you want me to do?
Okay, I want you to take the ratio of the pressures.
What ratio? B back over B node?
Yes, because that's the
No,
second.
there is no such thing as B back over P node.
You want your P exit over P star.
Excellent. B exit over B star. You get your free homework if you tell me where did you get your B star. Christine.
Your P star from whenever you do initials, if you have your M1.
Yes.
You get your P1 or
And Christine has a free homework problem. So Christine is that saying is that from the inlet, from M on, you can get your B1 over B star. And now you have your B star, and since it's the same B star throughout the duct, now at the exit, I mean you take this B exit, B star, and B exit over B star, this will allow you to get your M exit. So you have M inlet from the nozzle, you have M exit from the star thing. You got this, you plug it here, and we will have this chart for you by next class. You'll be able to find the chart. Right? Now take 15 minutes break and we'll start the exam at 7:10. Sorry, 6:10.